Good evening. I will wait for a few minutes and then I will start. Good evening. We will start the week 10 problems today. And myself Subham, TA for this course, Thermodynamics Classical to Statistical, which is taught by Professor Sandeep Paul, Department of Chemistry, IIT Guwahati. So in the last week, this Fermi gas was okay. In the last week 9, Fermi gas was taught, and now it was Bose gas and this Bose condensation and earth and para-hydrogen that were discussed in the week 10. So we will do some questions regarding that only. So before starting, we will revise some formulas and then we will continue our question answering. First we will discuss the Bose-Einstein distribution. So Bose-Einstein distribution, we have already discussed this, and here there is no restriction, like there is no restriction of how many particles can have in one state. So no restriction on particles, like there can be as many particles in a single state. And we know that Bose-Einstein distribution is followed by bosons, and these bosons are having integral spin, quantum number, like I is equals to 0, 1, 2 and so on. The examples are photon or all even number of fermions, like helium-4. The nuclei of helium-4 is boson, because it has 2 proton and 2 neutron in nucleus, so there are 4 fermions. This implies this is a boson. So nuclei of 4 helium is boson. And we know that psi for boson is symmetric. And that about the function, we know that it is equals to e to the power e minus ef minus 1 divided by kBt. So this is function f for boson, and this is equivalent to probability. So up to here it is the simple formulas. Now let's discuss it with temperature T. There is a critical temperature known as boson temperature. This is already discussed in class. And with respect to this TB, we study all these quantities. Like the formula TB for TB is 2 pi h square by mkb. This formula we are going to use in the question part. This is Riemann zeta function, epsilon 3 by 2. This is number of particles. This is the volume, and it is 2 by 3. We can write it as h square upon 2 pi. This h cut is, since h cut is h upon 2 pi, so this is h cut square by mkb. N by v is rho epsilon 3 by 2 to the power 2 by 3, and this Riemann zeta function at 3 by 2 is, this is equal to 2.612. Now we will discuss some other formulas. Total population, we will discuss this total population above TB and below TB. . for the temperature T greater than TB. Above this Bose temperature or this critical temperature, all the particles are in excited state. All the particles are in excited state for temperature greater than critical temperature, and for temperature less than boson temperature, particles gradually occupying the ground state. Let's say these are the excited states and this is the ground state. So the particles are all in, there can be many particles in one state. So all the particles are in excited state. There is no particle in ground state for temperature greater than boson temperature. But once the temperature start decreasing, the particles start to come in the ground state as well. Particles start to occupy these ground state level. They start coming from the excited state to ground state. So particles gradually occupying the ground state for temperature less than TB. Well, TB is Bose temperature or critical. Now about this Bose condensation. When temperature is below TB, these particles are coming to this ground state, and this series of quantized states, become very large, and discontinuous with the population of excited state. So this extra population is Bose condensation, Bose-Einstein condensation. So they are populating very fast in the ground state, and this extra population is Bose-Einstein condensation. And number of this number of particle in excited state can be calculated by this formula: V by 4 pi square 2m by h cut square to the power 3 by 2 and root of E divided by B e to the power E by kBt, and this B is a special function. This B is equals to, this is a function of temperature, and this is equals to either 1 or F inverse. This F inverse is again a function, and this we will write this also. Riemann zeta 3/2 Bose temperature divided by temperature to the power 3/2 for temperature greater than or equal to Tb, and 1 for temperature less than Tb, this B. So now this F inverse, here F is equals to 2 by pi 0 to infinity integration and root y divided by p e to the power y minus 1 dy. And Tb we know, Tb is Bose temperature or critical temperature. This is equals to T pi or h square upon 2 pi m kb n by Riemann zeta into V to the power 2 by 3. So again, now we get the population density in excited state when temperature is for normal temperature. Now for temperature less than Tb, total population in excited state N excited is equals to total number of particles divided by T into Tb, T divided by Tb to the power 3/2. And in ground state, this is in excited state. In ground state, N naught is equals to N 1 minus T by Tb to the power 3/2 for temperature less than Tb. So these are all important formulas. Now if we assume 0 ground state energy, if we say that E0 is equals to 0, ground state energy is 0, then particles in Bose-Einstein condensation make no contribution to total energy. So this say that if ground state energy we are taking it as 0 point energy is equals to 0, then this contribution from Bose-Einstein condensation particles is 0, and the total that we are getting, total energy that we are getting is only because of this excited state particles. So this will be equals to U internal energy, that is equals to integration from 0 to infinity and excited function of energy E dE. So this will become, for temperature less than Tb, it is equals to 0.77. I am just writing the formula, expression was already done in the class. nkBt T by Tb to the power 3/2. And for temperature greater than or equal to Tb, means at larger temperature, it is equals to 3/2, nearly equal to 3/2 nkBt. This is nothing, just the at high temperature it follow Boltzmann distribution. So it is according to the Boltzmann distribution. This is 3 by 2 nkbt. So this is the Boltzmann distribution limit has reached at high temperature. But at low temperatures, the formula for internal energy is this. Now about ortho and para hydrogens. So for ortho hydrogen, spins are parallel. And for para, spins are anti-parallel. Like there are two electron in hydrogen H2, so they can be both spin up or spin down. This is for ortho. Or they can have spin up down or down up. This is for para. And for this ortho, I is equals to half plus half. This is 1, and for para, I is equals to 0. Spin quantum number I is equals to 1 for ortho and 0 for para. And this is very important. For I 0 and 1, this J will be even for 0 spin, it means for para. This is for para, this is for ortho, and here the J will be even, and for ortho J will be odd, and 2i plus 1 spin density will be 2i plus 1, that is equals to 1, 2, 0 plus 1 is equals to 1, and 2, 1 plus 1 is equals to 3, and this W distribution, weight of distribution is 2i plus 1, that is equals to 1 into 2j plus 1, and here this is 3 into 2j plus 1. So this weightage of this para and ortho, this is 3:1, 3:1 distribution. We will do a few questions for this ortho and para hydrogen, so we will clear them there only. And now we start doing these questions. So question number 1. The volume of mole of liquid helium is given. The volume for 1 mole, this is for 1 mole, and volume is equals to 27 into 10 to the power minus 6 meter cube. So this is per mole. They have given it for a mole. Mass is given, mass of a helium atom. Only for one atom, this is 6.65 into 10 to the power minus 24 gram, that is equals to 6.65 into 10 to the power minus 24 into 10 to the power minus 3 kilogram. And this Planck constant is 6.62 into 10 to the power minus 34 joule second. And Kb and Na Riemann zeta are given, and we need to calculate the boson temperature Tb, and we know the formula h square by 2 pi kb mkb 2 pi mkb n by Riemann zeta function into v to the power 2 by 3. So all the quantities are given, and n here is Na. N is equal to Na for 1 mole of particle gas. Particle is Bose gas. So all the quantities are given, we need to just put the values and get the answer. So Tb is h square, this is 6.62 into 10 to the power minus 34 square divided by 2 pi 2 into 3.14 into mass is 6.65 into 10 to the power minus 24 minus 3, this is 27 into kb 1.38 into 10 to the power minus 23. So I have changed all the units in the same same units to balance this. This is in meter, this is in kg, this is in joule. So these are all balanced, so I am not writing here the units because these are already balanced. So n is Na 6.022 into 10 to the power 23 divided by Riemann zeta function is given, this is 2.612, and the volume is given 27 into 10 to the power minus 6 meter cube per mole divided by this is to the power 2 by 3. So we can solve it just by simply calculate this. Now just simply calculate this. Sorry. So where were we? This Tb is equal to 6.62 into 10 to the power minus 34 square, and this 2 into 3.14 into 6.65 into 10 to the power minus 27 into 1.38 into 10 to the power minus 23 and 6.022 into 10 to the power 23. This is plus, and this Riemann zeta function, this 2.612, and this volume 10 to the power minus 6 to the power 2 by 3. So we need to calculate this. So first I will solve this to all the powers, 6.62 square into 10 to the power minus 68, 2 into 3.14 into 6.65 into 1.38 into 10 to the power minus 27 plus 23, this is 50, 10 to the power minus 50, and now this. So quickly I will use calculator and calculate this. 6.022 divided by 2.612 and 27, this is equal to 0.085389 into 10 to the power 29 to the power 2 by 3. So, and this side 6.62 divided by 2, 3.14, 6.65, 1.38. So this is equals to 0.76 into 10 to the power, this is minus 18, and this will be 85, 1, 2, 3, okay. Let me calculate it again. Okay, so if I take 2 points here, this is 29, and I want to make it dividable by this 3. So if I multiply 100 here, it will become 8.5389 into 10 to the power 27 to the power 2 by 3. So now we can solve this. So this is 8.5389 to the power 2 by 3. So square and then cube root. This is 4.177 into 0.76 into 10 to the power minus 18 into, this is 9 plus 2, 10 to the power 18. So this is 1. So multiply it with 0.76. This is 3.175 approximately. So the answer is 3.2, close to this. That is equal to 3.2. So now we move to the next question. So among the following, at 0 degrees Celsius, hydrogen containing mainly para-hydrogen; at 0 degrees Celsius, hydrogen containing mainly ortho-hydrogen; at the liquefaction temperature of air, the ratio of an ortho and para-hydrogen is 1:1. At liquefaction temperature of air, ratio of ortho to para-hydrogen is 3:1. At room temperature, ratio of ortho to para-hydrogen is 3:1. At room temperature, the ratio of ortho to para-hydrogen is 1:3. Even at high temperature, the ratio of ortho to the para-hydrogen can never be more than 3:1. So first, since we know these properties of ortho and para, that is at 0 Kelvin, it is mainly para. So I think it is 0 Kelvin here. And at liquefaction of air, this is 1:1 para and ortho. This is 1:1. Para is this more stable form. At low temperature, this is thermodynamic stable. So this is only para at 0 Kelvin, and at liquefaction of air, this is 1:1, and at room temperature, At room temperature it is 3:1 ortho to the para, and at high temperature also it is 3:1. And we cannot get there is one very interesting thing in this, that we cannot get 100% ortho hydrogen. We can only get 75% of it, and we cannot get more than this. We cannot get more than, we can't get more than 75%. But we can have 100% parahydrogen. That is at very low temperature. So what I want to say, that we can have 100% parahydrogen at very low temperatures, but we cannot have 100% orthohydrogen at any temperature. We can only get 75%. So now we solve this. After having this, we can now easily solve this question. So we know the properties, we can only find the correct answers here. So at 0 Kelvin it is mainly para. Okay, this is the correct answer. It is mainly para at 0 Kelvin and not mainly ortho at 0 Kelvin. So this is incorrect. At the liquefaction temperature of air, ratio of ortho to para is 1:1. So this is correct. At the liquefaction temperature of air, the ratio of ortho to the para is 3:1. This is not correct. At the room temperature, ratio of ortho to the para is 3:1. This is correct. It is 3:1 only. At the room temperature, the ratio of ortho to the para is 1:3. No, this is not correct. This is 3:1, not 1:3. Even at high temperature, the ratio of ortho to the para can never be more than 3:1. This is also correct. At high temperature also, this is only 3:1. So what we have, this 1, then this 3, then this 5 and 7. 1, 3, 5 and 7. Sorry, 6. Okay, 7. So answer is 1, 3, 5 and 7 are true. Okay, so option C is correct. Question number 3. For the oxygen molecule in ground state, the value of psi rotation will be. So this is having I is equals to 0, and for I is equals to 0, J are even. J has even number, and for I is equal to 1, this is odd. So this is I is equal to 0 system, so this is only even. I just told that this, if I is equal to 0, this J is even, and if I is equal to 1, J is odd. And for here, for 0816, this is I is equal to 0 system only, so this is J is all even. For 1608 molecule in ground electronic state will be, this is whole atom. This whole atom is having even number of fermions. This implies this is boson. So this is only the molecule in ground state electronic state will be a boson. So the molecule in ground electronic state is this, the value of psi electronic. So electronic wave function is always antisymmetric. So this psi whole is symmetric, this whole is boson, the whole atom is boson, but the electrons are fermions. So if we are specifically talking about these electrons, the psi electronic will be antisymmetric, but psi for this whole atom is symmetric. So this is the trick here, that psi electronic for the electronic wave function is antisymmetric. Now question number 6. The volume of 1 mole of neon, so liquid neon is given, and the mass of neon atom is this. Assuming liquid neon is a ideal boson gas with 0 spin, okay, I is equals to 0, boson gas. The value of boson temperature will be, okay, this is again TB, we need to calculate. This is h square upon 2 pi m kBt, sorry, kb, n by Riemann zeta 3 by 2 v to the power 2 by 3. So by putting the value we can get the answer. This is h square 6.62 into 10 to the power minus 34 square, 2 into 3.14, mass is 27 into 10 to the power minus 24 gram, that is multiply by 10 by 3 kilogram, okay, and this kb is 1.38 into 10 to the power minus 23, n is again, this is for 1 mole, so this is 6.022 into 10 to the power 23, Riemann zeta is 2.612, and the volume is 54 into 10 to the power minus 6 to the power 2 by 3. So we need to calculate this only. So I'll use calculator to calculate this. This is 0.04269 into 10 to the power, sorry, into 10 to the power 29 to the power 2 by 3, and this is 6.62, 43.8244 into 10 to the power minus 68 divided by 233.9928 into 10 to the power minus 50. So let's take it as, this is as, let's take it as 4.269 into 10 to the power 27 to the power 2 by 3. So just solve this, 4.269 to the power 2 by 3. 2 by 3. So this is 2.63 into, this whole is 10 to the power 18, and here it is 50, this is 10 to the power minus 18, So this will again cancel out. This is in same in multiply only. So 10 to the power minus 18 into 10 to the power plus 18, it is 10 to the power 0, that is 1. So this 2.63 we need to multiply it with 43.8244 into 2.63 and divided by 233.99. So this is 0.492. 0.4925 this TB in Kelvin. So this is the answer, 0.49. So we'll move to the next question in 2 minutes, just a 2-minute break. Okay, so now we move to the next question. Someone is So we are here in question number 7. So what is the partition function for hydrogen molecule? So we need to calculate partition function in terms of this rotation partition function. Rotation partition function for hydrogen molecule. So first I'll write this general formula, and then for this expression of partition function for boson and fermion I will write, and then we will calculate for hydrogen. Q of rotation for this, let's say for boson first. For boson, this is Q rotation for boson is for n number of particles. This is I plus 1 to I plus 1 summation of j is even 2j plus 1. This is degeneracy of rotation. 2j e to the power minus j plus 1 h square by h cut square by 2 pi m kbt. This is h square by 8 pi square I kt. This is nothing but this is the energy E by, and this is the energy, this 8 pi square I, j minus j plus 1 h by 8 pi square I. This is rotational energy, and this is k divided by kbt plus I into 2I plus 1. Now again here summation of j odd, and for odd 2j plus 1 and same energy e to the power minus j plus 1 h square by 8 pi square I kbt. So this is the, for boson, this is the value of Q. And we can generally we can calculate it by like this. For boson, if j is odd, this is I into 2I plus 1 integral values, and for j is equal to even, this will give I plus 1 2I plus 1, and just this is the simple. For even we are using I plus 1 2I plus 1, and for odd we are using I into 2I plus 1. So by putting the values for hydrogen, we can simply get the value for Q R N, because this is for hydrogen, this is boson only, 2 H2, 2 ortho and para. These are 2 fermions make it a boson. So Q rotation is I is 0 for so this will be Q ortho plus Q para. So Q ortho so I is equals to 0 for ortho, so this is half plus half, this is 0, sorry, this is 1. I is equals to 1 for ortho, so this is I plus 1 plus 1, this is 2. Okay, there is some okay. For ortho j is odd, for ortho j is odd. We have just in the beginning I just told that for I is equal to 0 j is equal odd. So for I is equal to 0 j is odd, so this is the one, 2j plus 1, this is j is equal to 0. Okay, I am making some mistake, I guess. Okay, just put the value and then we'll calculate. So for I is equals to 0, this is 1. So for E1, this is summation E1 2j plus 1 e to the power, this is the energy of rotation ER by kBt plus, now put here the value for this I is equal to 1, so this is 2 plus 1 3 times summation of odd 2j plus 1 e to the power minus er by kBt. So this is the partition function for rotation in this hydrogen molecule. Okay. Now to the next question, what is the physical significance of Fermi energy? So Fermi energy, we have discussed this in the last class. So we now discuss the significance of Fermi energy. So first of all, fermions are half integral spin. They are having half integral spin. So let's say if we are talking about half spin at T is equal to 0 Kelvin. So we'll investigate the occupancy of state whose energies are less than or greater than the Fermi energy. Let there is a energy EF, and for the levels above and below, so we will investigate E less than EF and E greater than EF, and then try to find out what is the meaning. So for E less than EF, so since we know that F of Fd, probability of this occupancy, this is equals to 1 over e to the power E minus EF by kBt plus 1. So since we are saying that this E is, this temperature is 0, T at T is equal to 0 Kelvin we are talking about. So at T is equal to 0 Kelvin, this is E minus EF, and E is less than EF. So this is minus here. So this is e to the power, that is equal to e to the power minus infinity plus 1. So e to the power minus infinity is nothing but the 0. 0 plus 1, this is equals to 1. So what does this says, that at 0 Kelvin and energy less than EF, so below the Fermi level, all the particle lies below the Fermi level. So this probability is F of Fd is 1. This implies at this and temperature T is equal to 0 Kelvin. This implies that all the particles lies below the Fermi level at temperature 0 Kelvin. Okay, so now wait a minute. So okay, so what we get, the significance of this at T is equal to 0 Kelvin, E less than EF, all the particles lies below the Fermi level. So now for energy greater than EF, So now again E minus EF by kBT minus plus 1 for Fermi, F of E Fermi Dirac. So now E greater than EF, this is positive and this is temperature T is equal to 0 Kelvin, so this is 0, so this is e to the power infinity plus 1, so this is 1 over infinity, so this is 0. This means that there is not any particle above EF. So let's say this is EF and these are the other states. So there is no particle above this Fermi level, but all the particles lie below this Fermi level. So this is the significance of this Fermi energy. We just studied for 0 Kelvin, and for E is equal to EF, this F of E is equals to, for E is equal to EF, this is equals to at 1 over e to the power 0 plus 1, that is equal to 1 over 1 plus 1, that is equal to half. At any temperature, F of E is equals to half. This implies that probability of finding the particles is at this Fermi level is half. So this is the physical significance of Fermi energy. We can say that I'll just write this statement. So what we have concluded, at absolute zero, all energy levels up to Fermi level are occupied and none above. So this is what we have concluded. Now the question number 9. This is for Fermi gas. The question is calculate the Fermi energy of copper solid, assuming that each copper atom contributes one free electron to the electron gas in metal. So there is an electron gas, that is Fermi gas, and we need to calculate the Fermi energy. We know the formula for Fermi energy actually. EF is equals to h square by 2 m is mass of the particle, 3 by 8 pi n by v to the power 2 by 3. So the weight is given, this is 63.5 AMU. So this is gram per mole, you can consider. So for 1 mole mass is 63.5 gram, that is equals to 6.022 into 10 to the power 23 particles have 63.5 gram mass. Sorry. So what will be the mass of one atom? Mass of one atom will be 63.5 divided by 6.022 into 10 to the power 23. So we can just simply calculate this. 1 divided by 6.022. So this is equals to 63.5 into 10, this 1.66 into 10 to the power, this is 1 over 6.022 is equal to 1.66 into 10 to the power minus 24. So this is also this, we know what is this quantity. Okay, this is in gram actually. This is in grams. So this is 63.5 into 1.66 into 10 to the power minus 27 actually kilogram. So we know this quantity actually. What is this? 1 AMU atomic mass unit is equal to 1.66 into 10 to the power minus 27 kilogram. So this is this unit of converting 1 AMU to the 1 kg, and this is how it came. So we can use this from this mass of one copper atom. Okay, so we need to calculate this N by V actually, and we have volume. No, we have density. This is number density, but we have mass density. This is rho, mass upon volume we have. That is equals to 8.94 into 10 to the power 3 kg meter cube. Kg meter cube per meter cube. That is equal to mass is 63.5 into 1.66 into 10 to the power minus 27 kg, and the volume is unknown. So we can calculate the volume from here. Volume is 63.5 into 1.66 into 10 to the power minus 27 divided by 8.49 into 10 to the power 3. This is for one particle actually. So give me a minute. So this is, let me add, okay. N by V. I need to calculate this N by V. So volume should be, if we are considering this 6.022 into power, this is for, no, they have not, assuming that copper atom contribute 1, the density of this, the calculated Fermi energy of copper solid. So they are not giving 1 mole or something like this. So need to calculate it for 1 only. So for 1 particle, N by V is equal to, this is volume for 1 particle. Okay, yeah, we are doing it correct only. So now we are going in right direction only, so we just need to calculate, these values. I have put it here. So they are given only they are calculating Fermi energy of copper solid. Thus they are not giving any how many particles they are calculating. So we are calculating it for 1 particle. For 1 particle, N is equals to 1, and volume is this. So N by V is equals to 1 by 63.5 into 1.66 into 10 to the power minus 27, and this will go up 8.94 into 10 to the power 3. So this is n by v. This many atoms per meter cube. So now from here okay, we know n by v. Now from there we can calculate the value. So n by v is equals to 8.494 into 10 to the power 3 divided by, what was that, 63.5 into 1.66 into 10 to the power minus 27. This is atoms per meter cube. Okay, so EF was h square by 2m 3 by 8 pi v to the power 2 by 3. So this is equals to 6.26 into 10 to the power 6.62 into 10 to the power minus 34 square divided by 2. Mass of electron is 9.11 into 10 to the power minus 31. This is mass of electron, actually mass of particle, and the mass of particle here is boson and fermion, and this is electron, one electron. So electron is the mass we need, mass of electron we need here. So this is kg per electron. For each electron we are getting this. This is also electron per meter cube actually. Because there each atom is contributing one electron to the electron gas, so we can say this is electron per meter cube. So this is 3 by 8 into 3.14 into 8.94 into 10 to the power 3 divided by 63.5 into 1.66 into 10 to the power minus 27 whole to the power 2 by 3. So we just need to calculate this and we'll get the answer. So let's just simply calculate this. Quickly by the calculator. .8244 into 10 to the power minus 68 divided by 2 to 9.11. 18.22 into 10 to the power minus 31. This is 0.010128878 into 10 to the power, this is 3 and this is 2730. 10 to the power 30. Okay, to the power 2 by 3. So if we multiply with 3 zeros here, 1, 2 and 3, so this will become 1 2 3 10.12818 into 10 to the power 27 to the power 2 by 3. So this is into 3 zeros and square and cube root. This is 4.68 into 10 to the power 18, and this is multiply it with 43.8244, 4.68 divided by 18.22. This is 11. So this is coming 11.256 into 10 to the power minus 68 into 10 to the power 31 into 10 to the power 18. So this is 10 to the power minus 19, 11.256 into 10 to the power minus 19. Or so this is the answer. This is in joule. So this is the answer. We can convert it into electron volt also. So this is we know that 1 electron volt is equals to 1.602 into 10 to the power minus 19 joule. So you can divide it with this to calculate into electron volt. So 1 joule is equal to, so we can, okay, I'll erase this and just write the answer in electron volt. So this is energy is 11.256 into 10 to the power minus 19 joule, that is equal to 11.256 into 10 to the power minus 19 divided by 1.602 into 10 to the power minus 19 electron volt. So this is 11.256 divided by 1.6. This is 7 electron volt. This is the answer. Thank you. This is all I have for today's class, and I'll be here for a few minutes, 5-10 minutes, and if someone joins and asks me question, I'll be happy to answer them. Thank you. I'll leave the meeting in 5 to 10 minutes, and till then I will wait for if someone joins.